Building towering skyscrapers, installing massive pipelines, and paving vital roads witness the awe-inspiring power of construction shaping our modern world's future. In modern multi-story steel construction, extending the height of columns is unavoidable, and this is achieved through a process known as column splicing. A column splice is a structural connection that joins two shorter column sections to create a continuous member. Since columns cannot be fabricated or transported in extremely long lengths, they are delivered in manageable segments. Consequently, splicing is necessary to assemble these sections on site and to maintain the structural continuity of the building frame.
10 inches. Rumor. A good time called Jim, it says in the bathroom. Cable down, and hold that.
To begin with, the purpose of a column splice is twofold. On one hand, it enables the extension of column length by connecting prefabricated segments. On the other hand, it ensures structural continuity by allowing the column to behave as if it were one continuous piece, rather than two separate elements. As a result, the column can reliably transfer vertical and lateral forces from upper floors to the foundations without any weak points. Therefore, splicing is not just a matter of convenience, but a critical structural requirement. When it comes to types of splices, several methods exist, including welded and bolted splices. However, in practical building construction, bolted splices are by far the most common for site assembly. This is because bolted connections are faster to install, easier to inspect, and less affected by weather or working conditions. Thus, bolted splices have become the preferred solution in most high-rise projects. In a bolted splice connection, the assembly is achieved through the use of steel plates and high-strength bolts. Specifically, flange plates are attached to the flanges of the column sections, transferring axial and bending forces. At the same time, splice plates or web cover plates are connected to the web of the column, allowing shear forces to be transferred effectively. In this way, the combination of plates and bolts ensures that all types of forces, axial, shear, and bending, are safely transmitted across the splice. Moreover, the tightening of bolts provides sufficient clamping action, which improves friction between plates and further increases the load-carrying capacity of the joint. In addition, the design of a bolted splice must carefully consider load transfer. The splice is required to handle not only the axial load from the building weight, but also bending moments caused by wind or lateral actions, as well as shear forces arising from floor slabs. For this reason, engineers must calculate bolt sizes, plate thicknesses, and spacing precisely to guarantee safety. Furthermore, the location of the splice plays an important role. Equally important is the consideration of seismic design. In earthquake-prone regions, column splices must meet strict requirements to ensure that the building can withstand seismic forces without failure. For example, design codes may require a minimum shear capacity or compact detailing of the connected members. Additionally, bolted splices must be detailed to allow ductile behavior, so that the structure can dissipate seismic energy rather than fail suddenly. Moreover, bolted splices offer several practical advantages during construction. They allow for rapid assembly of steel frames, which reduces construction time and labor costs. Because bolts can be pre-installed in the plates before lifting, site workers only need to align the column sections and tighten the bolts. This efficiency makes bolted splices highly suitable for tall buildings where large numbers of connections must be completed quickly. Additionally, inspection is straightforward since bolted joints can be visually checked, and torque tests can verify the correct tightening of bolts. Consequently, quality assurance is much simpler compared to welded joints. In conclusion, column splicing is a fundamental process in multi-story steel building construction, and among the various methods, bolted splices stand out as the most practical and efficient solution for on-site assembly. By using flange plates, web plates, and splice plates secured with high-strength bolts, engineers ensure the safe transfer of axial, bending, and shear forces between column sections. The construction site of the Walterdale Bridge in Edmonton, Alberta, one of the most ambitious and challenging engineering projects in Canada in recent years. Behind the construction fence, ironworkers pushed themselves to the limit to build a bridge that would not only replace an aging century-old structure, but also stand as a modern engineering landmark. Hey. From the very beginning, the project presented unusual challenges. Edmonton, known as the Gateway to the North, experiences some of Canada's most extreme weather conditions. With the brutal winter quickly approaching, every day became a race against time. The team of local 720 ironworkers knew that once ice began to choke the North Saskatchewan River, their window of opportunity to move and install the massive center span would close. Nature dictated the pace, and any mistake could mean severe injury, death, or a delay of several months. The new Walterdale Bridge required an investment of more than $150 million. And the expertise of an international team of engineers and skilled workers. The centerpiece of the project, a 1,000-ton steel arch span, had been built on land over the course of 8 months. Floating such a structure into place on 2 barges and positioning it precisely between 2 towers demanded both detailed planning and flawless execution. For the ironworkers, even being off by 1/8 of an inch at the base could translate into inches of misalignment at the top. Precision was everything, and there was zero room for error. Before the arch could be moved onto the river, the crew had to assemble a critical support system known as the red iron. This red-painted falsework served as a temporary skeleton to hold and brace sections of the bridge during installation. Raising and connecting these steel members required courage, focus, and strength. At times, workers had to walk narrow beams 56 meters above the icy river, balancing tools and equipment while fastening slippery braces. The job demanded not only physical power, but also mental toughness, as fear had to be faced head-on. Many ironworkers had survived close calls, slips, and falls in their careers, yet their commitment to feed their families and contribute to something lasting pushed them to climb back up and keep working. The camaraderie on site was essential for survival. Ironworkers often joked with each other to relieve stress, reminding themselves not to take everything too seriously. At the same time, when the moment came to work, discipline and concentration prevailed. The pride they felt in their trade was evident. Many expressed satisfaction, knowing their children and grandchildren could one day point to the bridge and say, "My father built that." Hosha. As the project advanced, another major challenge emerged: the river itself. Barges intended to carry the arch upstream frequently became stuck in shallow waters. To address this, dredgers were brought in to deepen the riverbed by removing rocks and sediment. The delays were frustrating, especially with ice forming earlier each day. Despite setbacks, the crew pressed on. After overnight dredging, the barges finally moved upstream, clearing the path for the monumental task of sliding the greased arch span onto them. However, every stage carried risk. If water levels dropped too low or the ice thickened too quickly, the barges could become trapped, jeopardizing both the structure and the workers. Supervisors and engineers had to decide whether to proceed or wait, weighing safety against the immense pressure of deadlines and costs. When the day finally arrived, ironworkers donned full survival suits, preparing for the worst as the barges carried the steel arch into the middle of the river. Every cable, winch, and skid shoe had to perform perfectly under the enormous load. Meanwhile, other crews worked on shore to modify skid shoes, which would serve as the landing pads for the arch once it was lowered into place. With the ice closing in, the atmosphere was tense, but the workers' determination never wavered. As the barges crept forward at barely a meter an hour, the crew guided the span into its final position. Aligning the arch between the two towers required extreme precision. This was the most stressful stage of the entire project. Slowly, carefully, the ironworkers made adjustments until the span sat exactly where the engineers wanted it. The moment the structure touched down, the team received the order to weld and bolt everything securely into place. When the arch was finally set, a wave of exhilaration swept across the site. Years of planning, months of struggle, and days of racing against weather and nature had culminated in success. The ironworkers had once again proven their resilience and skill, completing one of the largest and most complex lifts in Canadian bridge construction. Although much work remained before the Walterdale Bridge was fully complete, the most difficult and dangerous task had been achieved. For the ironworkers of Edmonton, the Walterdale Bridge was not just another job. It was a legacy. They had battled time, weather, ice, and engineering challenges, all while facing the constant dangers of their trade. They demonstrated strength, toughness, and camaraderie, showing the world that ironworkers truly are the men and women who build the structures we live with every day. As one worker put it, there is no better feeling than walking high in the air, placing steel into position, and later stepping back to admire the monumental structure that will stand for generations. The Walterdale Bridge now connects the city with a graceful arch of steel, a symbol of engineering progress and human determination. Behind its elegant design lies the sweat, courage, and pride of ironworkers who risked everything to bring it to life. The Panama Canal, opened 101 years ago, has long stood as one of the greatest engineering milestones of the 20th century. By connecting the Atlantic and Pacific Oceans, the 80-kilometer waterway transformed global trade, reducing distances between production and consumption centers. Since its opening, more than 1 million vessels have transited the canal. To meet modern demands, the Panama Canal expansion, the most ambitious project in recent years, began in 2007 and culminated with its inauguration in 2016. The centerpiece of this expansion is the third set of locks, which includes 16 rolling gates and 152 valves to regulate water flow. Water-saving basins were introduced, reducing water use by 7% per lockage. Over 4.4 million cubic meters of concrete were poured, and extensive dredging was carried out in the Culebra Cut and Gatun Lake to accommodate Neopanamax vessels. New dams and channels were built, requiring the excavation of nearly 50 million cubic meters of material. Beyond engineering, the project also prioritized sustainability, reforesting more than 900 hectares and relocating over 5,000 animals. The expansion strengthens Panama's role in global maritime trade, ensuring safe, efficient, and environmentally responsible navigation for generations to come. The construction project on State Route 520 near Medina is a major infrastructure improvement aimed at enhancing safety and traffic flow. It includes widening lanes, upgrading interchanges, and improving connections to local roads. Additionally, the project strengthens bridges and adds modern safety features, ensuring long-term durability. This development plays a key role in supporting regional mobility and community growth. Taiwan's semiconductor manufacturing company is undertaking a massive construction project in Phoenix, Arizona, with an investment of $40 billion. The company is building 2 advanced semiconductor fabrication plants, representing one of the largest foreign investments in U.S. history. The scale and complexity of the construction are enormous, involving cutting-edge technology and extensive infrastructure. These facilities will strengthen domestic chip manufacturing, reduce global supply chain risks, and support innovation across industries, marking a significant milestone in the semiconductor sector and U.S.-Taiwan industrial cooperation. The installation of the Titan pump jack scaffold system begins by assembling the Titan frame and attaching the workbench to the pump jack on each side. Once completed, insert the poles into the system. Poles are available in different lengths and can be connected with pole connectors up to 48 feet in height. For stability, use non-skid bases on flat surfaces or spiked anchors on uneven ground. Next, attach the support braces to the structure, positioning them with the swivel heads to fit various wall or roof conditions. After installing the base ends and braces, ensure the poles are level and properly braced. Then, place the standing platform and secure it by threading the safety chain through the rungs. Repeat this process for the work platform, confirming that both planks are firmly attached. To raise the scaffold, step into the stirrup and push down until the platform rises, keeping the surface level. Install the safety net to protect workers and prevent objects from falling, and add an end rail to comply with OSHA standards. Finally, to lower the system, press the brake lever with your foot until it clicks. Then turn the adjustment handle to bring it down evenly. The process of constructing a diaphragm wall begins with boring, which is the most critical and time-consuming stage. A trench is excavated in the ground using specialized hydraulic grabs or trench cutters, guided by a bentonite slurry that stabilizes the soil and prevents collapse. The excavation progresses in panels, typically several meters long, to the required depth, which may reach dozens of meters depending on design. The slurry is continuously circulated to remove excavated material while maintaining trench stability. During boring, depth and verticality are carefully monitored with instruments to ensure the accuracy of the trench. Any deviation is corrected immediately to avoid structural issues later. Once the required depth is reached, the trench is cleaned using a desanding unit to remove suspended solids and ensure a clean surface for the next stages. After boring, reinforcement cages are prefabricated and lowered into the trench by cranes. These cages are carefully aligned and connected when deeper or longer cages are required. Proper spacing is ensured to allow concrete flow. Next, stop ends are installed at the trench ends to shape construction joints between panels. These elements, usually made of steel or PVC, define panel boundaries and allow sequential excavation and concreting. Finally, concreting is carried out using the Tremie method. Tremie pipes are inserted to the bottom of the trench, and concrete is poured continuously under slurry to avoid segregation. As concrete rises, slurry is displaced and collected for reuse. This ensures a dense, homogeneous wall panel with strong structural integrity. The installation of a 72-inch double-barrel reinforced concrete pipe storm drain begins with careful site preparation and trench excavation. A trench of sufficient width and depth is dug to accommodate 2 parallel lines of RCP, ensuring proper grade and alignment for stormwater flow. The excavation must be stabilized and compacted to provide a firm base for the pipe bedding. Next, a layer of granular bedding material is placed and leveled to create uniform support. The CAT 365 excavator is then used to lift and position each heavy RCP section. Pipes are carefully lowered into the trench, with crews guiding them to achieve precise alignment. Joint connections are cleaned and sealed to ensure watertight performance and long-term durability. As the installation progresses, the second line of RCP is placed parallel to the first, forming the double barrel configuration. Continuous checks are made for grade, spacing, and joint tightness. After all sections are joined, sidefill and backfill materials are compacted in layers around the pipes to provide structural stability and prevent settlement. Finally, the trench is fully restored, completing a robust storm drainage system designed to handle high-capacity flows efficiently. The reconstruction of the I-57 roadway begins with preparing the base and setting up forms to define the edges of the pavement. Workers carefully place the forms, ensuring correct alignment and elevation to guide the shape and level of the new roadway. Once the forms are in place, chairs are positioned to hold the reinforcing steel at the required height. These chairs create a stable support system that ensures the reinforcement remains embedded at the proper depth within the concrete. Next, steel reinforcement bars are arranged across the lane. The rebars are tied together and placed according to design specifications, providing strength and durability to the new pavement. Particular attention is given to spacing and overlap, as these directly affect the structural integrity of the finished slab. After the reinforcement is secured, the site is inspected to confirm all components are properly installed before proceeding to the next stage. The concreting phase follows with the arrival of ready-mix trucks. Concrete is discharged into the prepared lane, either directly or using conveyor systems. Crews spread the concrete evenly, ensuring it flows around the steel reinforcement and fills every part of the form. Vibrators are used where necessary to eliminate air pockets and achieve full consolidation. The concrete surface is then struck off using a mechanical screed that runs along the forms, leveling the material to the specified grade. Immediately after screeding, the surface undergoes floating to remove imperfections and embed aggregate particles. This step prepares the slab for subsequent finishing operations. Workers then use long-handled bull floats and other tools to refine the surface, creating a uniform texture. As the concrete sets slightly, hand finishing begins. Crews edge the joints, create proper grooves to control cracking, and smooth the surface of the lane. These hand operations are essential to achieve both durability and ride quality. The construction progresses lane by lane, with each section receiving the same careful sequence of form setting, reinforcement placement, concrete pouring, and finishing. Once a lane is completed, curing measures are applied to retain moisture in the concrete. This often involves spraying curing compounds or covering the surface with plastic sheets. Proper curing is crucial to achieving the designed strength and preventing premature shrinkage cracking. Finally, after curing is completed and the concrete has reached the required strength, forms are removed and the edges are checked. Any minor surface adjustments are performed manually to ensure smooth transitions between lanes. The result is a structurally sound pavement, finished to high standards through a combination of mechanized operations and precise handwork.